Welcome to the MIDRC monthly seminar series. Today, we're very happy to have Professor Sanmi Koyejo speaking to us. Let me tell you some about him. So Professor Koyejo is an associate professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign. He spends also some time at Google as part of the Google Brain team. His research interests are in developing the principle and practice of trustworthy machine learning. Additionally, he focuses on applications to neuroscience and healthcare. Professor Koyejo has been the recipient of several awards, including a Best Paper Award from the Conference on Uncertainty in Artificial Intelligence, a Skip Ellis Early Career Award, a Sloan Fellowship, an NSF Career Award, a Kelly Fellowship, and an IJCAI Early Career Spotlight Award. He's also received a training award from the Organization for Human Brain Mapping, and he serves as the president of the Black in AI organization. We are very happy that he is able to join us today and give us a talk on towards algorithms for measuring and mitigating unfairness in AI. Bias and diversity and mitigating unfairness is a major part of MIDRC, and we welcome his contributions today, and I will pass this on to him. Welcome.
Thanks, Mary Ellen, for the kind introduction. Let's share slides now. Okay. So hopefully that shows up well, and I'll go ahead and get started. So again, it's a real pleasure to speak to this group today. My talk today will mostly focus on algorithmic foundations of thinking about measuring and mitigating unfairness, with an eye towards methods that might be useful for various applications. And I'll highlight some of these as we go along. So quick disclosures. So as I guess many in this group and broadly MIDRC been thinking about, there's clearly a shift in how we think about the nature of data and algorithms that we might deploy, specifically thinking about healthcare applications, but more broadly, the nature of data and the implications of algorithms deployed in the world. And specifically, I think the general feeling was making decisions based on data somehow give you a clearly unbiased view on the problem. And so this was a way to get around, if you like, human biases. I think now it's much clearer that biases follow the data, if you like, and algorithms will often take on biases of the designers, biases of the data collection, and so forth. And so thinking carefully about the nature of different kinds of algorithmic biases that we don't want in our methods, I think, is becoming a pressing problem. There's lots of evidence of these issues in the literature. I'm showing here some work led by Bolomwini and Gebru in 2018, where they called the Gender Shades Project, where they evaluated a variety of existing published methods, some of these in deployment at the time, that were meant to do, in this case, I believe, a gender prediction kind of task. And they compared different demographic groups and showed that the methods they developed could have quite different outcomes depending on the demographic groups that it was applied on. And this kind of disparity has implications downstream for the use of these kinds of methods. Of course, beyond the broader AI frame, there's also specific instances of issues with algorithms specifically deployed for healthcare applications. So there's now growing evaluation, growing understanding of issues, both of issues where we have data from, I guess, behavior showing disparities sometimes across groups. But I think even more concerning now when we implement and deploy algorithms, showing that these algorithms can often exacerbate issues of disparities across groups. Now, the issue of unfairness that's driven or sped up by AI algorithms, I think, is quite a complex one. And there are many places where we could imagine intervening. I'm showing here a figure from Chen et al. In 2020 that I think does a pretty good job highlighting the various aspects of what it means to deploy an algorithm. Here, this paper is targeting healthcare applications, so very relevant for the talk today. And so they talk about thoughtfulness in problem selection and how we can have biases in problem selection that affect the kinds of problems we choose to solve, which can have downstream effects on different groups. There are, of course, biases, as many of us know, in data collection, specifically different kinds of minority subgroups having less data collected, particularly when we go with convenient samples. But even without that, different kinds of biases that can crop up in data collection that can create issues in the algorithms that we might implement and deploy downstream. There are some interesting questions on how we define what we want our methods to do, and I'll talk about this a little bit today. I'll talk, of course, about algorithm development. That's the main topic of the talk today, though I'll take a fairly narrow view and maybe deep dive in one class of methods that I think might be interesting for many in this group. And finally, how we think about evaluating the method after we've deployed it. And I think maybe more importantly, having ways of thinking about continuous evaluation over the life cycle of algorithms deployed in the world. So, of course, this is quite a wide breadth of potential intervention points. For my talk today, I'm going to take a narrow-ish view and partially also based on my background and the kind of work that I do. I'll mostly talk about two cases or two parts of this pipeline, if you like. I'll talk about this outcome definition question and some ways, some recent developments in thinking about how to implement and select metrics, particularly when it pertains to fairness of AI methods. And then I'll talk a bit about some class of methods on the algorithm development side that I think are interesting for helping to think about mitigating unfairness questions from deployed AI systems in healthcare. Thinking about algorithm development and mitigation, the machine learning AI field has broadly settled on three broad approaches for mitigation. The first of these is what is known as pre-processing. The idea here is that I take my data and I'm going to adjust the data in such a way that the adjusted data has removed some of the issues with respect to unfairness. So the mitigation happens at the input data stage. So I'll actually spend quite a reasonable amount of time talking about this today, specifically talking about some of the representation learning methods that are designed to address these specific kinds of issues. Another class of methods are what are known as in-processing methods. These are methods that jointly implement the machine learning pipeline, so the predictive pipeline, and within that pipeline have constraints or regularizers that try to improve unfairness violations, so try to mitigate unfairness violation as part of the machine learning training pipeline. And then there are also post-processing methods that take existing deployments or existing predictions and then reason about how to adjust the predictions to mitigate some of the issues with unfairness in the already implemented, deployed predictive pipelines. In the talk today, I'll mostly talk about some existing work in pre-processing, and I'll defer to offline discussion or maybe questions. But my lab has done some work on both in-processing and post-processing as well. I'm happy to talk about those or some other methods and maybe even trade-offs between these approaches for implementing mitigation of unfairness issues. Within the pre-processing pipeline, a very interesting framing of the problem is one by McNamara, Ong, and Williamson, where they think of this issue of representation learning as or pre-processing as thinking about the task separated into three roles. So the first role they define is the role of a data regulator, whose goal is going to be twofold, and I'll expand on the role. But the idea is that the data regulator takes various kinds of fairness criteria, the learning goal, the data that you have as inputs, and then produces some signal that can be used by a data producer whose role it is to implement the actual representation learning process. And then based on the representation learned, the data user can then implement a predictive model as one would normally do in the machine learning pipeline. So in a bit more detail, as mentioned, the data regulator, their task is to determine fairness criteria, determine data sources, and eventually audit the results of implementing this fairness pipeline. So their input is the data, and then the outputs are both, like I said, criteria, and at the end, potentially models when they're auditing. The task of trying to figure out fairness criteria, as you might imagine, is one that's challenging. But there is increasing awareness of the difficulty of this problem and a variety of different methods that are being trialed, if you like, on thinking about how to intervene on how we pick fairness criteria. Part of these questions includes thinking about who we should be asking. So what kinds of interaction should we be using to help select the right fairness criteria? Should it be, what kinds of stakeholders should be experts, judges, policymakers, and other potential stakeholders, potentially patients, clinicians. I'll, at the end, touch a bit on the idea of auditing at the end. So once you have a fairness criteria and you have a pipeline for implementing machine learning in applications, part of the role of envision for the data regulator is also to audit the results to check whether the methods have implemented the goal as set out at the beginning. So to give a bit more context, I'll dive into one approach that we've been building for thinking about this metric selection problem. So to give some background, which will also be useful background for the rest of the talk. Many of the ways that we measure what machine learning models do, particularly when we're building classifiers, can be summarized into something known as the confusion matrix. So the confusion matrix, if you haven't seen it before, is a fairly straightforward mathematical summary or population summary of the behavior of a model. In a binary classification setting, the binary classification task is to construct a model that gives predictions of one of two options. In this case, I'm representing these by either 1 or 0. And the ground truth are themselves also 1 or 0. And so given the setup, you can make, you can summarize the predictions in 4 ways. You can have true positives, false negatives, and true negatives. The positives and negatives are highlighting the prediction of 1, and then the correct predictions being true positives and true negatives, and then the mistakes being the false positives and false negatives. And many of the ways that we measure the performance of machine learning methods can be summarized as some function applied to this confusion matrix. Now, I mention this because this becomes useful when thinking about fairness of machine learning methods. And one large class of ways that the machine learning community has put together for thinking about group fairness is thinking about fairness are methods or metrics known as group fairness metrics. And the idea here is that you take your entire population, you divide your data into perhaps the sensitive subgroups that you're looking to measure. And then you implement and deploy your model for each of these groups. And you can then measure differences in model prediction across the different sensitive subgroups. So commonly you'll see work looking at accuracy differences, like I highlighted at the beginning, between different subgroups. But then there are a variety of additional metrics that have come up. So metrics like equality of opportunity, which look at true positive differences, true positive rate differences across the different subgroups as the way that we're measuring performance. Or in this case, unfairness mitigation in a deployed machine learning method. Now, some of the challenges that show up and might be obvious once laid out in this way are that there are now a variety of different ways that you could pick. Even if you restrict yourself to the group fairness framing, there are a variety of different ways that one could imagine evaluating what fairness might mean. What makes this even more challenging is that you can show in practice, because of time, I won't go into detail here, but there are now many examples where fairness metrics can actually contradict each other. So optimizing for one measure can actually lead to worse performance in a different measure, which leads to the question of how one might select which measure or which statistic or which metric you should equalize across different groups if one is looking to mitigate unfairness in a machine learning method. One approach that my group has been working on is an approach we're calling metric elicitation. Broadly, the idea is that we want to query stakeholders who might have intuition about what they would like machine learning methods to do, but not necessarily clear ways of quantifying the behavior as a function that you can then throw into a machine learning pipeline. And the idea here is that we want to construct a process by which we can make it easy for practitioners or stakeholders to specify the preferred behavior of machine learning methods. The rough idea and the way that this works is that they construct a sequence, our procedure constructs a sequence of queries, and I'll give an example in a couple of minutes. And based on these queries, we can then try to nail down the class of measures that best agree with the responses that we're getting from the stakeholders. A bit on the results. So we've shown some good mathematical properties of this approach. So for instance, if you're looking just at linear metrics, so these are metrics where there's an asymmetric cost for false positives and false negatives, we've shown that using the approach that we've developed, under some set of weak assumptions, you can very quickly get a very good handle on actually fixing the numbers of the relative cost of a false positive error versus a false negative error. And we've extended this idea to a variety of additional settings. We've explored various kinds of noise issues, and I'll invite you to look at references or maybe chat offline on some of the details and other applications that we've been exploring on the conceptual side. We've also explored this in practice. So I'm showing here some early implementation of a pilot study that we recently completed, which we're building up into a complete evaluation with colleagues out of human-computer interaction, where I'm just highlighting here what the preference measurement looks like. Here we show users two kinds of models, stakeholders two kinds of models, which are illustrated in ways that are designed to make it somewhat intuitive to reason about the classifier behavior. And then we get a measurement of preference between the two. So it's meant to be a relatively low cognitive load task to the extent possible. And based on the preferences, we can both very quickly nail down approximating notion of metric, so some measure that agrees with the preferences. And also we can evaluate how well we're doing compared to new kinds of queries that we might ask in the future. Again, I'll defer to discussion or offline for more details on this approach. So we're talking about the data regulator in this process. And as mentioned, its other task is to audit the process of the overall pipeline of fairness mitigation. And so this can be done by auditing the representation, as I'll talk about in a couple of minutes, or auditing the entire process at the end. So auditing the final model to see if you've actually achieved the fairness mitigation goals that one is interested in. The data producer, as outlined in the representation learning framework, has the task of taking the fairness criteria and the original data and then converting this into what is known as a representation. And this representation is what is then pushed forward to be used for the actual machine learning task. So the idea of a representation is that you take your data and you convert it into some other form, often low dimensional, though I'll talk about cases where the data is of the same size as the original data, but where some of the bias has been, potential bias that's related to unfairness has been removed. And there are a variety of approaches. You're likely familiar with principal components analysis. There are other classes of methods like autoencoders, which give you nonlinear approaches for trying to construct data transformations. So the idea is that the data producer takes the input data, fairness criteria, and then creates some representation where you have mitigated potential fairness risks from the original data. So there are lots and lots of approaches to do this in the machine learning literature. This is a quickly growing field, and pros and cons of a variety of different kinds of methods. I'll talk about one method that uses a adversarial approach to try and mitigate fairness issues. Here specifically, the goal is to try to decouple the sensitive attributes from the input data, to construct a new data sets where the sensitive attributes are decoupled from the original data. This is probably best illustrated with an example. So I'm showing here data that comes from somewhat low resolution face image data sets, where the goal here is to decouple male, female labels from the face images. And so, as you can see in some of the highlighted examples, different here facial characteristics like mustache, for instance, is removed from the image as one of the, say, key facial characteristics that may be aligned with one or the other male or female label. Here, somewhat a cartoon example, this model and models that have come up after it have also been applied to both tabular data, image data of different kinds, to show how one can construct feature transformations to take your input data and then try to remove sensitive information as part of the information that the data actually contains. And here I'm showing just results. The thing that the knob that one can tune is the strength of, I guess, how much fidelity you want to keep. So how close you want the original data to be to the transformed data, which allows you to trade off potential downstream performance, which is what is shown here, compared to the fidelity of and potential fairness mitigation measured by a distortion. As mentioned, this is one of a variety of methods. Broadly, they all try to do a similar thing of finding a data transformation that removes sensitive attributes from the original data. The final step in this pipeline is the data user. And this approach is interesting because the data user is set up so that they don't deal directly with the fairness question. So the fairness responsibility is pushed to a different part of the pipeline, and the data user can just implement standard machine learning pipelines on the data as you would normally do, yet have a better fairness mitigation than if they use the original data as is. So to summarize the pipeline, the idea is that there are roughly 3 steps in this pipeline. There is a data regulator, and their goal is to determine the fairness criteria, determine the data sources, and eventually audit the results. Once the criteria are selected, and I talked through a metric elicitation approach for selecting criteria, this information is pushed to the data producer, which takes the criteria and the original data and constructs some transformation of the data, shown here as a representation that removes the sensitive attribute information. This is then pushed to the data user, which now has a quote unquote sanitized data set that they can then use to build the machine learning pipeline. And then based on this pipeline, the data regulator can again audit the results to see if the initial goals have been met. And this is can be a good pipeline when you already have maybe good expertise on the data user side. So you have folks, for instance, who are quite good at building machine learning models, but don't necessarily have the expertise to think about some other fairness criteria. And so this is interesting because it separates the roles into different steps. And so you can have different expertise at each of these steps that can then solve aspects of the task and push the results to the next step. Okay, so of course, there are lots of open questions. I think there are some hard questions about the extent to which quantification is the right approach for thinking about fairness. It makes a lot of sense in machine learning settings because a lot of algorithmic methods are very tied to quantification. and metrics. And so it's sort of a key component of most algorithmic methods. But I think there are some maybe interesting conceptual debates to be had about whether that's the best approach for thinking about fairness questions broadly. There are, I think, interesting questions that are not yet answered about who the stakeholders should be and how one might combine your preferences. So clinicians, patients, advocates, and how one might combine different ways that they might think about fairness in a particular application. There are interesting questions on the data producer side. I mentioned one algorithm for fair representation learning. It has some good properties, but I think this space is still open for additional innovation. And of course, the data user, where the potential, one of the issues that can come up that's separate from the standard machine learning pipeline is that depending on how, while the framework is set up to make, if you like, their task easy as a straightforward machine learning process, there are ways to game the system unknowingly, if you like. And so this is known as, or lingo for this is fairness leakage, where additional information potentially or other sources can now recorrelate your predictions to sensitive attributes, even though you've put in all this effort to decouple. And so there are questions on how the data user can avoid things like fairness leakage. A bit more broadly, I hope I've at least somewhat shown, or at least highlighted, how challenging the issue of fairness is within algorithmic systems broadly. And I think specifically in healthcare, this is a challenging and tricky issue with lots of open questions. But there's a large community that's thinking about these questions and working towards trying to come up with solutions for various aspects of these questions. A large multidisciplinary community in particular, which I think is heartening in this case. There are some interesting open questions, challenging open questions that relate to delayed impacts of algorithmic systems. So typically it might not only show up at prediction time, the effects can be downstream after a long process. This leads to issues in measurements that makes the problem more challenging. Questions of intersectionality that make some of the algorithms I've described a bit more challenging in terms of how to implement them, issues of data size for intersectional subgroups. There are hard questions that come from the fact that in many cases, we deploy machine learning methods in healthcare in feedback loops, where the deployed machine learning system is used to collect new data that we might use to maybe fine tune or improve our model. And those feedback loops are known to have significant negative effects on machine learning pipelines in general. So this is, I think, an open problem where new tools are being developed to try to address. As highlighted at the beginning, often the data source is the initial, most visible, if you like, source of bias that might lead to unfairness in the downstream machine learning pipeline, say due to sampling effects, undersampling of different subpopulations. And often it might be the easiest place to intervene to help improve unfairness issues in the machine learning pipeline. Lastly, I want to mention an idea of being careful when we think about fairness issues in deployed algorithmic systems. We want to avoid what has been termed fair washing. So broadly, issues of unfairness that we might identify and remove from a system may not imply that the system is fair in a broad sense. What it means typically when we mitigate a known set of unfairness issues is that we've mitigated the fairness issues that we have identified so far. However, new issues can come up because once you deploy a system, all of what I've highlighted so far can lead to issues in downstream deployment or new issues that were not identified at the beginning. And so part of this is, I think, the auditing piece and evaluation of deployed machine learning systems to keep an eye on potential new issues that can come up and think about this as a development process as opposed to a one-time sort of check mark that we give to our algorithmic systems. So that's most of what I had planned to talk about today. I think we're moving on to questions. It's yeah, I'm excited to answer questions that you might have.
Okay, thank you. That was a very exciting talk, and it actually gives us a lot to think about as we work through a lot of data in MIDRC. So I have a question for you. I'm trying to see how to implement this data regulator, data producer, and data user within the MIDRC setup. And as I think about that, you may have it all set up for a specific task, such as diagnosing COVID positive and negative. And you have this data out there, and you put the data out there and you say it's sanitized, it's good to go. Someone then comes along and downloads it, and they only download the COVID positive cases because they're interested in prognosis and looking at the really sick patient versus the not so sick patients, the severity of the disease. You have to start, how do you know that everything's task-based. So now you have to reconstruct everything. How does that work?
Yes and no. It depends on, so nominally, no. I think the place where it gets challenging is the fairness measure that you might be using and the extent to which that measure ends up having correlations between the thing you want to predict and the sensitive attributes. So what's the representation learning class of approaches, what they try to do is they try to remove the correlation between the sensitive attributes and the input data. So what this would look like, for instance, in say, let's say, X-ray images would be that you sanitize by removing correlations between, say, X-rays and race, as an example of what you might try to implement. And if the measure of fairness that you're most interested in captures that property, then this may be sufficient. And this should be sufficient for different kinds of predictive pipelines, assuming no other data comes into the system. And so this is, I made this slightly, I pointed this out a little bit at the end, where often in predictive pipelines, with, say you've sanitized the data as outlined, one might imagine adding additional sources because you want to make your prediction better. And these additional sources of data that you might add later on may recorrelate your prediction. So they may induce new kinds of unfairness issues, even though you've removed it from, say, the X-ray images. So that's typically where this pipeline can break. This approach has a lot more flexibility to changing the task. It's however a lot more sensitive to changing, like adding different data sources, for instance. Now this comes at cost, I should highlight. So this is not free, nothing, trade-offs. So the cost is, it tends to give a little bit less of fine control of, if you like, performance to mitigation trade-offs, because this is all done at the beginning before you've constructed any of the machine learning. At least the mitigation is done before you've implemented any of the machine learning pipeline. So this can be good for sort of large-scale deployments with maybe lots of different people, like data release, as we're talking about, but can be challenging if you, say, want to have finer-grained control for various kinds of applications.
Okay. I have more questions, but folks, if any of you have a question, just type it in the chat and we'll bring it up. I think it's a great opportunity having Sanmi right here. So I was thinking about the data regulator. Is that can be done? And when we develop AI, I always like to think like the human and figure out how they would be thinking. So for the data regulator, is that something that can, do you work it through manually and then try to make it automatic? Or will the data regulator, can it function separate from the task?
It can function separately. A similar answer, if you like. Okay. So it can function separately from the task if there is some knowledge that downstream, well, you need two things for it to function separately from the task. You need that no new data is going to be introduced. It's going to introduce new kind of correlations downstream, and that sort of everyone downstream follows some they follow the sort of process that you prescribe, specifically that they so the next step in the process has to use the fairness metric that you've prescribed, for instance. That's maybe not as critical a piece, because one is hoping that you're developing this in a sort of coherent way where the different pieces are looking to work together. I think you're correct to highlight that the regulator piece right now is maybe the most involved, or at least the least clear on what to do. So this is where, like particularly thinking about the metric selection, I think is still an open problem. And then the auditing, I think, is also super important. And one can imagine auditing that can be quite involved, even though sort of on the surface, it's a straightforward sort of measurement kind of task. So beyond those two pieces of the how to pick the good metric and then the auditing at the end, it tends to be, again, as long as no new data is coming in, the class of methods that have been developed are designed to be mostly task agnostic, even though, again, you do this comes at some loss of flexibility.
Okay. Is there is there a good example? I think a lot of people will learn by example here, and yeah. A real life example where all these three have been implemented. You know, for example, if someone wants to learn about a performance metric in a binary classifier, they can go learn about RSA analysis, and you can walk them through them an example. Is there one out there that we can refer attendees to read through?
So I think a lot of these, the pipelines, short answer is maybe no, that's public that I'm aware of.
Not yet.
Not yet, maybe is the right answer.
Okay.
I'm aware of, so there's of course a lot of work where people have very carefully thought through what fairness metrics they might want to use in a particular setting. So that line of work is reasonably, well, at least there's existing work there about different stakeholders or problem settings and what good measures might be. I think the extension of this to, say, the metric elicitation approach that I just talked about, which tries to automate some of that decision-making process. Automate in a sense of speed up, so convert it from, I guess, convert from intuition to a quantification. That part is still a bit early. So we're doing work on this and we're sort of at the pilot stage. We're not yet in sort of fully deployed stage. But the concept of having this separated out task of a part of the model that determines what the right metrics are, I think that's fairly reasonably mature, even if the implementation is not fully there. I'm not aware of public implementations of sanitized data sets. There are a fair amount of algorithms, and I guess I've had conversations with groups that have done things internally that include constructing representations that mitigate unfairness, but I'm not aware of something published in public that I can point to, unfortunately, for that role. I'll say, I think there's probably still more work to do on the algorithmic side there as well, for it to be, I guess, as stable as one would like for easy deployment. So I think that's still a place where there's still some algorithmic questions open about what the best ways of doing this and what the trade-offs are. But I know that their implementation is just not papers I can point to. The last step is standard machine learning, so that last step is easy, or at least yeah, lots of examples of that last step. Right. But I think you're right. There's not as many examples of the full pipeline, even though I think it's an appealing pipeline, which is why I presented it.
Okay. Well, I don't see any more questions. This has been great food for thought. Oh, there is a question. Yes. Can you elaborate? This is from Marie. Can you elaborate on the post-deployment for deployed algorithms that have not undergone any unfairness mitigation? What are the key pieces needed for post-deployment fairness quantification? It's in the chat.
Yeah, that's an excellent question. So again, I think often the most challenging step in practice is how one chooses to measure unfairness. And I generally argue that it's a good idea to measure, but I pointed at the end there to this. I think it's a good idea to think of measurement as a key step in thinking about fairness mitigation. So from that point of view, I think the task then is to take a deployed machine learning system in a particular context, have examples of the machine learning predictions, and then evaluate based on some fixed measure. So examples, for instance, would be, say, if you choose accuracy as your measure, and you want to see how accuracy differs across different population subgroups. And that becomes the way that you're measuring, post-deployment, you're measuring the model behavior and potential fairness issues. Outside of that, I think there are some infrastructure pieces that can make this work well. So I highlighted this briefly, but I think the best case scenario of post-deployment evaluation is, again, not to think about this as a one-time thing, but to think about this as a continuous thing. So what changes over time is our understanding of fairness issues evolves over time, and we want to have ways to think about continuously measuring as post implementing and deploying a model. Demographics can shift over time. So a model that had reasonable behavior when deployed in, say, a certain maybe majority focused, or maybe a balanced population, and then the population shifts, demographic shifts over time to not be as balanced, and that then leads the algorithm to have very different behavior over different subgroups. So that's, again, another reason why we might want to continuously measure what our models are doing. There are these feedback loop effects that I pointed to briefly, this idea, again, that often most models often have to be updated over time because, as I mentioned, demographics, or say seasonality is a big effect in measuring or predicting something that's related to, say, the flu as an example. A simple example of where seasonality might make a big difference. And so that might end up showing up in our predictions. And if this shows up again, we want to have ways of, over time, as the model changes, continuously evaluating what the model is doing.
Okay, thank you. I find this, it brings up a lot, will bring up a lot of thinking. And I hope that some of these you can implement, test out within the MIDRC umbrella. And if you need help doing that, we have a whole crew of folks who are probably extremely interested in this, because this is extremely important. On behalf of all, I'd like to thank you for this. And we look forward to our next monthly seminar. Thank you all.
Thank you. Thanks, everyone.